Good morning. Yeah, as always, just totally changed my schedule. So this will probably be more for YouTube, I'd imagine. But what we're doing today is continuing through Sandy Maguire's great book, Thinking with Types, and this chapter is Existential Types. God. Yeah, and we'd previously gone quite a way through. If I'm going to click the right one there, how far through did we get? We got through to 7.2. So I think we kind of made our own dynamic. Let's have a little look what it was. So we did we explained a little bit more about the for all. We had this where we're able to constrain the t of this gadget to show, and then we did some little tricks and numbers with that, and then ultimately it came to we did the lift d2, didn't we? So we did it like a lift. Is lift d2 still in here? There it is, yeah. And that was basically, we were trying to make a dynamic version of a language, like when you use plus, and you can ultimately use we created a function just called pyplus, like Python, and ultimately you could just use plus in multiple different scenarios. You can do a string with a string, so we'd use that, and then we can do an int with an int, so we'd use that. But then when we started mixing them together, like a string and an int, we had the ability to allow for that to happen also. So that's pretty cool. Oh, and then we experimented with a balls, just for lols, just to prove that also worked. Okay, and then we thought, well, okay, why not? Was it in this one? I thought it was in this one. Let me see. No, so we got there. So we did the X type applications. Yeah. So without signatures. So we kind of this one we had to default to in the REPL because of the num class. Yeah, so we wanted to constrain the num class in the REPL. And we got these to work. Yeah, because if you look, if it where was the return? Maybe dynamic here. So the return, if it fails, obviously we don't, if any of these fails for some reason, well, we want to have the ability to return a maybe. And that's what we essentially did. And then the majority of, I'll use the word magic, happened inside of cast. And that's where it did a lot of the cool stuff in cast, which you can see is used here. From dynamic is used here. Okay, and then we experimented with that. We did some from dynamic string, and then we did we did from dynamic. We expect, because every time you do an at, ultimately you're filling in this a or in the constraint. So there we're saying, well, we want the from dynamic to constraint to be the a to return a maybe string ultimately, and we do pi plus dynamic for and dynamic minute, and then that had recognized the fact that they'd be an integer, or sorry, an int and a string, and then it adds them 4 formats. Cool. And then when we messed around with other stuff, obviously we got a failure and it returned nothing. And I thought this part, so where is that part? Because I thought we did play with that, where we were able to abstract them out, but I don't see it here for some reason. Is there oh no, we did, we totally did that. Yeah, here I put it further up because I was reusing it. So instead of before, we used to have we used to have hash show and hash show where the constraint was here on the left to what the t was. So you'd have to have your own every time. So what we were saying, well, why don't we try and abstract this bit out and make that available as a value? And this is what has does. It literally puts the constraint inside the top and it calls it C, and it's saying it's a function from type to constraint. And then we create this gadget and we call it has. It has a constraint of C to T, and the t is the value that we pass in, and then it has a hash t. Okay, so sorry, we pass it there, and then that means that it returns a constraint. So what that means then is when you see it in use, a little bit further down, there. So type, which are these two. So you can see that we're saying has is actually, has show is has, and the constraint is show. So ultimately what that then means is that, yeah, we've got this is now available to use with any type you want to give it. You get a dynamic of it, which is cool, isn't it? And that's that. And then we sort of change these to represent that. So we have a has, yeah, and we carried on with that. And then we did as isMempty. So we started playing actually. So with isMempty, and this is where we ran into troubles with monoid a EQA. So it was saying, unfortunately, there's no type level lambda syntax. So we're unable to turn this into something that's curryable. And then we can try type synonym. And there it was. But again, that didn't work because GHC weren't allowed to construct has monoid EQ. The problem is that the synonym must always be fully saturated. Yeah, so for this, the right-hand side must always be fully saturated, but it wasn't because we never know what the A is until it comes in. So it wasn't happy with that. So it said then, but fortunately, there's a solution for constraint synonym through though not the type synonym in general. We can instead define a new class with a superclass constraint and an instance that comes for free given those constraints, and it's simply that. I say simply, it's that. It's not quite that simple, is it? Which is monoid a EQA, the constraints, and then we've got monoid EQA, which is kind of like, if you look at it there, it's kind of try to attempt to do that, but clearly we've put it as part of the class constraint, and then the instance we do exactly the same thing. So this is known as constraint synonym. Okay, and then you can play with it. I think we did that. Yeah, and I think that's literally, and we stopped there. We had a go, it worked, and then we stopped and we got to this point. I think I'm going to keep going in the same file. I don't. Should I, or should I start a new file? Oh, okay, hold on. I'm going to start a new file because then at least. So chapter 7. What we'll create a file. What should we call it? We'll call it chapter 07, and it'll be 7.2. Oh my goodness. Should we call it scoping? Yeah, that's a little bit nicer, isn't it? What we'll do is, okay, yeah, we'll do that. And we'll do module. Hey, you go, Christian. Look at them emojis. Honestly, you're always coming through the powerful emojis. I need to zoom it in. It's like a sword and a helmet. Hey, Sue PP, how's it going? Yeah, again, just randomly changed my schedule. I was bored this morning, so I thought I'm going to do some of this and try and keep going. Look what I'm doing. Module, and I'm just typing in what the import is. The module is going to be called chapter. Is it 07? Except it's going to has to be like this, isn't it? Oh my goodness. Vince, want an interesting idea for a function to implement using typable? Hell yeah. You were talking about that. I want to see what you did. Well, it might have to be maybe a gist, a gisty gist, because why? Because Twitch is terrible with formatting code. I forgot what I'm doing. Yes, here we go. 07. No, we can't have it. So I've named it wrong already. I'm going to have to rename that file. But it's okay. Where? Okay, so let's copy, sorry, backwards. Go backwards. BB. Yeah. C. B. Okay. Save. Oh, hold on. You've given me already. Well, that was quick. Not what I was expecting, I'll be honest. 7. I'm coming. Okay, that's happy. We're going to rename this though, because that will not be happy. There we go. Everything's happy, I think. I don't know. Did we add it to... I can't remember. Yeah, we did do that one, so that's cool. So now, hopefully, if we do an error, it'll say it's got an error. Except... yeah, that was a good one. Good exercise. It totally threw me, and I felt dumb, but nice one. Okay. I keep saying a lot, because that's really thrown me. That's what happens. You see, technically I knew all that, and I said, you know, I had all the parts. Typo can help. It sure can. With a slight caveat that you have to be able to dictate what. Well, you have to, you know, give it some types. You have to feed it types. Stop being negative, Vince. You're learning. God damn it. How are you meant to entice others into Haskell if you're there struggling? I'm not really. It's okay. I guess it's that level of uncertainty that you have. Oh, unsafe. You gonna come in? If you can spell it properly. Unsafe perform. I thought it was on here. Whoops. IP. Okay, so it's happy with it. That was a bit weird, wasn't it? Okay. Existential types. Existential types can be used to prevent... Hold on. Are you actually learning Haskell if you aren't struggling? Does the tree make a sound if no one's there to observe it? I don't know. It's a trick question, I think. That's what you're giving me there, Gil Christian. Yeah, I do. The thing is there's a great... There's a thing actually about learning. I'll show you, because he's actually really good. A neuroscientist. And he explains, well, when occasionally, hold on, he's on Twitter, I think. Occasionally, Josh Rogan did have some good podcasts when he's not got morons on. Yeah, no, another detour. It's not going to be long. It's not going to be long. I've just got to find this person. I don't follow many people on Twitter for this exact reason. I've just got to remember his name though, which I can't, so that's helping. Where was it? Oh, damn it. Doctor something. Maybe he's calls himself Doctor something? DR? DR. No, that's bringing in wrong people. Oh, I thought I followed him on here. Oh, was that? No, it's Alex. Oh, he's really good. Ultimately, whilst I'm looking, is what he's saying is when... There he is. There he is. Okay. Check this guy out, because he has like a really nice concept about learning, and ultimately, for learning, the bit that's the hardest, because as you get older, obviously learning isn't... it's called... is it called laxive flexibility of the mind? And ultimately, we're built in that once we get, well, you know, genetically, once we get past a certain age, that flexibility of learning becomes harder to achieve, because what as humankind we're kind of like, okay, well, you know, you've achieved all the bases to not die, so just keep good at them. And then so what we get is this real sense of like, you know, things are terribly hard for a while, and then it's only once you get to a certain mind frame or state that then you can start actual learning and bringing things in. But the thing that puts a lot of people off is that initial difficulty, that sense of like failure, which is like natural, and it's all to do like your chemicals that your brain releases and all sorts. Yeah, it's really interesting, but it's trying to remember that that's a fact. You're struggling because you're learning and something good's actually happening, and once you go over that, then you'll get there. But yeah, but with doing Haskell and this sort of stuff, it is, for me, especially because I'm not academic or mathematician, it's on a daily basis. So I'm constantly like, eesh. Even though when we look back at the other example we gave, it was, you know, it's quite an easy one. I totally had it. But I get like that when I get to interviews as well. If I get an interview, they'll go, implement, and I'll just be like, oh, what? And my brain just goes, there it goes. Sort of like, it's gone. Bye. Just flies off and goes, you know, things that you've learned. See ya. So that's probably why I was never academics. I didn't do terribly well in exams. Yeah, because I'm just not. I don't know. I don't really learn a lot. So yeah, there you go. Right, back to track. I'm gonna do this with my glasses. They've gone a bit like, these are like those teacher glasses where they go into sunglasses form naturally, because there's actually a bit of sun for once. Yeah, it looks like I've got slight shades on. That's what's happened to me. I'm like a school teacher. So, existential types can be used to prevent information from leaking outside desired scope. So I had a read of this last night. Yeah, it's I think this explanation I was starting to get, but the bit that I think it's going to make sense. I didn't have it because I didn't have the computer when I was doing this. I was reading it, which is definitely not a good way of doing it. I really wanted to run these and look, because I've seen the ST, because the ST was in the book Concurrent Programming in Haskell, I think. No, it's Concurrent and something Programming in Haskell. Yeah, they used the ST because ultimately the ST monad can sort of perform side effect, I guess. You'll see. Well, immutability. It just writes over stuff. There it is. Parallel and concurrent programming in Haskell. Yeah. I should have probably not read that when I did. Or I haven't finished it, let's be fair. This is what happens. I get to concepts and I'm like, okay, this isn't too bad. Okay. And I'm like, oh shit, I'm lost. Right, okay, go back to the basics. Back to the basics. That's what I keep doing. Right, for example, it means we can ensure that allocated resources can't escape the pre-specified region. So I guess when we mean the region, it's like where this resource is in. So we can use the type system to prove that HTTP session tokens is quarantined within a request context, or that a file handle doesn't persist after it's been closed. So yeah, so like, you know, if you're grabbing a file or something, then you don't want it to keep going once you've closed it. So because existential types are unable to exist outside from their quantifier, we can use it as a scoping mechanism by tagging sensitive data via an existential type. Yes, I saw this. I think I saw an example of this in Matt Pearson's book. He goes on about, I think he uses this to do admin. So some information, some people can get access to admin, but in a different way than this. Actually, it's probably nothing to do with this, because this is to do with immutability. Let's keep going. The type system will refuse any attempts to move this data outside of its scope. Cool. Haskell ST monad is the most famous example of this approach, lending its name to the approach, the ST trick. Okay, if you're unfamiliar with it, ST allows us to write stateful code. There we go, that's the one. So it allows us to write stateful code, including mutable variables, which is what you tend not to do in Haskell at all. But the idea is if you keep it wrapped, so this is what I was going to say, to perform computations, so long as the statefulness never leaves the monad. So yes, you're getting this statefulness, but the safety you get from the fact that it won't leak outside of the monad. So in other words, ST allows you to compute pure functions using impure means. It's like a... No, don't say what it's like. Keep going. The amazing thing is that ST is not some magical compiler primitive. It's just a library code, and we can implement it ourselves. Cool. Assuming we're comfortable with using a little unsafe perform IO. Yeah, I'm comfortable with that. The word unsafe means do it. Of course, this is not a comfortable situation. Unsafe perform IO is fundamentally unsafe. It's in the name. But observe that there is nothing inherently unsafe about mutable variables. It's not the presence of mutable variables that makes code hard to read, to reason about. Yeah. So long... Oh, something just flashed. There's no lightning outside. That's freaky. So long as as all its mutations are kept local, we know that a computation is pure mutable variables on their own and do not cause us to lose referential transparency. So I think referential transparency is what you get from having things be immutable. I've just worked out what that flash is. It's windows outside opening on car doors or something, hitting the sun and then hitting the window, then hitting my eye. Referential transparency is lost when code relies on external mutable variables. I kind of want to have a quick look if there's like a simple Java. No, we're not. Should we say Haskell? But I guess it's not relevant to just... Oh, okay, here we go. This is going to say something. Referential transparency is an oft-touted property of pure functional languages, which makes it easier to reason about behavior of a program. I don't think there's any formal definition, but it usually means that the expression always evaluates to the same result in any context. Side effects, yeah. Like uncontrolled imperative update breaks a desirable property. C and ML are languages blah 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 blah. So show us an example. Yes, which prints ha ha ha. In an attempt to factor out repetition, we write yeah. So I get it. So ultimately, it's every time. So things like map. When we do a map, we're not going to adjust our input. We're not mutating our input list, for example. Okay, that's cool. I thought that's what it meant. Is lost when it relies on external mutable variables. Doing so creates an invisible data dependency between our code and the state of its external variables. Oh, here we go. Referential transparency means if you write name equals expression, it means they are the same thing. Ah, okay. So name equals expression, it means they are the same thing. Okay, that makes sense, I think. Oh, no, I'm going to ask you a question. So name of what? An expression of what? I'm like, I think I get it. Then I'm like, name an expression. Like name of... Yeah. Name? Expression. I'll keep going. And then... Yeah, you can answer what it means. See, I feel like at the first hurdle. Referential transparency means if you write name and expression. Okay, yeah. So what's name and what's expression? Right. It is... okay, where were we? Referential transparency is lost when the code... Yep. Doing so creates an invisible data dependency between our code and the state of its external variables. It is these cases, and these cases alone, that we need to worry about. As such, it's completely safe to have immutable variables so long as you can prove they never escape. The SC trick exists to prevent such things from happening. Enough jibber jabber. Let's implement it. At the heart of the SC is just an identity monad with a phantom S parameter. Oh, blog post. Here we go. Oh, you wrote a blog post about it. Sweet. Nice. So, substitution of sequential reasoning. I mean, that title, you get points for that. That's well good. I'm gonna keep that, and then I'll have a look through it. Nice. Ah, loads of code examples. 2 thumbs up right there. What did you use? Look at that. Powered by Hablog. That's a Haskell blog, I'm assuming, isn't it? Oh, I've not even spotted. Oh, look, you've got loads of other little blogs. Cool. I like it. Hold on. I think I saw that before. Nice. Look at that. Since 2014. You're killing it since 2014. Nice. Okay. Thank you. I'll definitely have a look at that. Though I'm lost now. Where was I? Here we are. Okay, we're going to create this new type. I like it. I like blog post with code examples. So I get to a certain point and I'm just like here, it's just like, you know, when I read loads of stuff, I just think, right, enough of the jibber jabber. I just think that throughout. Which is not good. Look where I'm writing ST. Just have it there. Okay, so we're gonna do all sorts here. There we go. Okay, thank you. Unsafe run st, and that's gonna be a. I mean, technically, let's just pump it all on this line, shall we? So it probably doesn't look as nice as it. No, I'm having it, doing it. Don't care. Notice that at 1, yep, so this part, we have a phantom type parameter. So we've got this S. So it's going to talk about, yes, S. This variable exists only as a place to put our existential type tags. We'll better see how it's used in a minute. Okay, so it's just there. So when you pass st 2 values, it's going to go, don't care. I'm using there. And that's when you unsafe run st. So that's when you're like grabbing the value out of the monad. Okay. So, okay. Applicative and monad instances could be provided for st to ensure that our unsafe quotes. I was going quotes like that, but I meant that. IO is performed whilst it's actually still safe. These instances must be explicitly strict. This is not necessary in general to perform the ST trick. It's only because we will be using unsafe perform IO for this example. No, let's do it. So instance, and we're going to do functor, and that needs an STS. So we're saying don't care about the S. So we've got to do an fmap for functor. And we'll do an sta equals. Okay. Yeah, this is what I wanted to look. Seek a dot. I need to see where seek was coming from. What is seek? More to the point. Oh. So it ignores. It gets an A and a B, and it ignores the A. So it ignores the A. Oh. And what's the... This is A to B. That's going to be an A, so that's going to be B. ST of B. So the fmap is ST of B. Give it the A. And just return the B. So what is the expected... So here should be like FB, shouldn't it? The expected return. STSB. Oh, okay. STSB. B. So we need that S, don't we? So in doing seek, if we go back, seek is STSB. So we know we've got B. A's been ignored. So what's at this point? Does it show us? Yes, here we go. So there we're doing, look at this magic. We're doing a function STSB to STSB, B to STSB, which is what that's done. And then we're passing in a B, and that returns us STSB. Okay, sweet. What's our F? A to B. Okay. Yeah, I'm still a little, what's happening with that phantom type? Because it kind of like, if you look at here, the types, like at this point, and that compose. So we know we've got for all BCA, BC, AB, AC. Yeah, so that's our compose. But we're still passing around that S. But technically, we're never really, so if you look at that, that's ST just takes one value. So how come the S is still being passed around? I guess that's because it's a phantom type. But to call it, yeah, so when you go to its constructor, it's only got one value, which is A, which is of A. Okay, let's keep going. Instance applic. This is always a fun one. Find the applicatives like gets really confusing, and then the monad's really easy after the applicative. So pure is just, yep, that's fine, and this one is going to be the fun one. So we're going to apply to STA, and that's fairly similar, except we're going to seek the F, and we're going to have to seek the A, ST, and that's going to be FA. Okay. So what are things at this point? What's going on here? So at this point we've got an STSB, and that expects an A to B. Oh. Oh, no, hold on. I'm going the wrong way, aren't I? Yes. B. Oh, am I? So ignore, sequence ignores its first value? A, yeah. Okay, I'm going to have a look at seek. So it's throwing me a little bit. Seek. Ah, I kept pressing the wrong thing. I guess it's going to be that one. So seek. The value seek AB is bottom if the A is bottom. Okay, and otherwise equals to B. In other words, it evaluates the first argument to a weak head normal format. Sequence is usually introduced to improve performance by avoiding unneeded laziness. A note on evaluation order: the expression seek AB does not guarantee that A will be evaluated before B. The only guarantee given to seek is that both A and B will be evaluated before seek returns a value. In particular, this means that B may be evaluated before A. If you need guarantee, blah blah blah. We don't need any guarantee. A to B. So yeah. So these, it doesn't even use them. They're literally Why are they there? Why is it needed? If it doesn't use F and A, but we use it here, is it to make sure that they definitely have run by the time it's got to here, so then this can be evaluated. That'd be my guess. That would be my guess. Let's keep going. Instant monad. STS. Where? What are we doing? STA, and we're gonna. What are we doing? Oh, I've lost my keys. Here we go. Bind to F, and that equals. Find a key. Thank you. Seek. A. FA. Yeah, I need to understand what seek's doing. I could. It's just checking if F evaluates. Actually, what might help? It won't help, but we'll look anyway. Oh no, we can't. It's built in, so we can't even look. That's it. Its implementation. Tough titties. You just got to deal with it. So, mutable variables can be introduced inside of the ST monad. For our implementation, we can simply implement these in terms of IO refs. We'll wrap them in a new type. Okay. So, we'll do a new type. ST ref, and that's an S and an A, so it's got the same. It's got the same S that's not being used. And please go away. Come back. Eventually it worked. STREF. Okay. I've got a feeling that this is where things are starting to go downhill. Okay, pay attention to the fact that stref also has a phantom S parameter. Yep, I did see that. This is not accidental. S acts as a label, irrevocably knotting an stref with the st context. Okay. That created it. We'll discuss this after a little more boilerplate that is necessary to get through. Okay, function wrappers for stref around IORef are provided, each of which unsafely performs IO. For example, we'd like to be able to create a new ST. Okay, let's create a new ST. So I guess we want to do that. New ST-ref. And that's an A to a ST of S. Ref SA. Wow, okay. New ST-ref equals. So now we're going to like get into the nits. ST-ref. Unsafe. Perform IO. And don't do a comma. New IO-ref. So new IO-ref. So we're using like IO-ref. So that takes an A and returns an IO of IO-ref. And then we compose that with unsafe perform IO, which expects an IO A, which is what we're getting. So our IO is our IO of IO-ref is that's our A. And then here we're just going to return after unsafe perform IO, we're just going to return IO-ref. And then we're going to stick IO-ref into ST-ref. Yeah, so it'll be ST-ref IO-ref. And then ST-ref IO-ref of A. And then we're going to pure, so wrap it in ST S of ST-ref IO-ref. Is that what it tells us? No, it doesn't. It'd be good if we could. What about here? What about here? Oh, well, I can see the type. I wanted to see the type. There's like a little trick you can do, isn't there? like that. I think if you go here, can you? Oh no, you can't. Sometimes you can. Oh no, it gives you down here. Look, look, look. Here we go. Oh no, it doesn't. It doesn't tell you. It tells you just type above. I wondered if it was a. Hey, hi, hello, hello, hi, hi, Haskell. I'm having an early stream, and to be honest, a bit of a struggle. Trying to work through this ST. Okay, well I've got this. The problem is I read this. Look at that. This is the back door. don't read anymore. Okay, well I think that's not too bad. So whatever we pass, obviously we're doing we're composing everything. So our A is going to straight go into IORef, and that's what we're going to perform. Because that returns an IORef of A. Yeah. And then from here, that'll be an IO. That expects the IO of IORef of A, and then that returns us the A, which will be IORef of A. And then here we'll pop it in stref, so it'll be stref IORef of A, and then we'll wrap it in the st. So we've got this thing inside, and these are just phantoms. They're just there for lols, and then we've got an A. Sweet. So let's read st. Read stref. Yep. I guess it'd be similar. Should be. SA. Oh no, we're passing it. We're giving it an A. Oh, of unit. So stref SA. Take an A. Return an st of s unit. Oh, okay. Read stref, and oh, this time it because it'll need a ref because I guess the ref will be in a different location. So we'll want a pure, so that wrap things back up. We want an unsafe perform IO. That one. We want a write. Whoops. IO ref. Okay. And then here, unsafe. What do we want? S. Oh, okay. We're doing the s ref to the ref. Let's have a look. So unsafe ref came from our. Let's pull this down. Actually, let's just. I don't know why I've got open that on the left. So if we look at unsafe ref is here. Unsafe. No, it's not from there at all. So unst ref must be coming from IORef. Okay, that makes sense. But ultimately, it takes an st ref, s of A, and then it returns an IORef of A. So it's getting that out of there. It's giving us the A back. Yeah. Okay. And then from there, we want, oh well, we can see it, an IORef of A and an A. Oh, hold on. Okay. So, because this is our, let's have a look. IORef of A, that's the output. It goes into IORef of A and another A. Don't know where it's getting the other A from. Huh, odd. And yeah, what's with that? So look at this. Unsafe ref, we're passing it. What's our ref? Our ref is an st ref of s of A, which is that. That's fine. That goes into it, and then it's an IORef of A is what it returns, and then that goes into here. But then that expects an A. Okay, don't know where the A is coming from. How come that meant? Yeah, is it because of the composition? No, we'll keep going. And then unsafe, so that grabs the IO, returns IF, and then yeah, okay. Well, hold on now. What are we at this point? Let's have a look. Oh, we're just dealing with IO of unit. We're just passing IO of unit around. And then at this point, we're doing unit to STS of unit, A of unit, and then we'll return STS of unit. And then, yeah, that's at this point. STS of unit, STS of unit. I think you took the wrong signature. Of where? Of this one? Of this one. Right, IRF. Is it showing the wrong one, do you think? I should have noticed that. You message, that is. Yeah, because it's clearly only got one input, hasn't it? But then you'd think that that'd be the A. Oh, the read stref. Hold on. Have I typed in the wrong word? No. Right. Oh, the read stref has the right stref signature. Ah, yes. Well, that makes sense. Sorry, everyone. I've literally, yeah, I don't know what I'm doing. Oh my god, I could just tell you. And implement it. I've just named it the wrong file, haven't I? I'm just writing. Oh my god. Well, the good thing is if you can learn from someone else's mistakes, you're onto a winner. Right, that's where the extra A is coming in. Hold on. I've got a thing for this. I remember. There it is. I'm just going to do this. Oh, my wife's back from painting. She's been painting a post box. So I wonder what's happened there. I'll get rid of this face. Go away, face. There we go. Where are we? Here. stref of SA. ST SA. Is that right? Yes. Right, we're back on track. Oh, that was painful. Except that's even more painful. Okay. Right, so that makes sense now. So that takes an ST, SA, IO ref. Hold on, more importantly, why was the other one compiling? I've not refreshed this in a while, I guess. Haskell language server didn't have my back. Because look, we had it like this before, something like that. I don't know what was going on. Yeah. Probably why I was getting a bit confused. Okay, so we can see that. Yeah, that makes sense. We've gone over this. We've gone over that. And then now we need a modify. So modify. Let's go up a bit. Both, yeah, they compile now. But I think the type signature that I had before shouldn't have compiled. Because you remember I was looking for an A. But in the type signature we didn't have it. So I think I had this type signature for this function. Or something like that. I don't know what I did. I did something advertedly stupid. But what can you do? It's how I was born. Can't do anything about it. Sorry, guys. stref. What are we doing? We'll go SA and then we'll go A to A. Yes, we expect a function and then. Oh, so this is modify. Yeah. So that makes sense. So we want to like modify stuff. So we're going to pass it a function, especially when we call it modifus. Okay. So modify. There it is. stref. And that takes a ref and an F. And we're going to do a little do. Do. Read stref of ref. Yeah, so we're getting our st. So we're using this. Read our stref. Get our st out. And then at this point, hold on. Because this is where there. So if we look, our type of A is, we just get the type A out. So read stref, we're passing it an stref of SA, and then that returns us an st of SA, and then we're grabbing that A out by left binding, which is cool. And then here we want to then write it. So we're getting the value out of st, and now we want to write over the top of it. Which is bad. Don't do this. Or do this in specific scenarios. So write stref, if we remember, it takes an stref. Yes, it takes an stref and an a, and then our a is going to be a to a. So whatever function we give it that does a to a, which can be any sort of manipulation things, which is going to be f. Well, sorry, the result is going to be, because write stref takes a ref, which is our original ref there, and then we read that ref, get the value out, we've got an a, and now we're going to apply something to that value, give the original ref, and write it back in. So write ref will then deal with the ref we're dealing with. So that's why we're mutating it, because really we're not like well, we're grabbing a value out of ref, passing along the same ref, and saying write something in it, and tough titties. That's it. We're overwriting it. And now, and finally, we provide a function to escape from the st monad. This is merely unsafe run st, but with a specialized type signature. Isn't that up here? Unsafe run st. Except we give it. Oh, okay. Let's have a look how this type signature changes. Oh, okay. So we've got our for all is going to be from within. So we'll have to call this slightly differently. STSA, and then so that's a function. I know. Oh, so it's literally just. Okay, that's interesting. Yeah, so for all s's, I guess this is that's where the magic is happening. Unsafe run st. Sweet. So unsafe run st. Okay, so that literally just grabs that value out. But we've got this constraint here. Well, not sorry, we've got this here, haven't we? The s. I'm sure that's gonna thicken the plot. So at 1 we are introducing. Oh, Yordi. At number 1 we are we see the introduction of the st trick. I thought it would be. This bit I've got a feeling. The type for all s to stsa indicates that run st is capable of running only those st's which do not depend on their s parameters. Oh, okay. See, I'll just look up for a while. We will discuss why exactly this works. Okay, phew. Glad I didn't have to try and work it out, because I couldn't. Shortly. But let's first convince ourselves that run st lives up to its promise. We can write a safe usage of st, one which will take state, compute a pure value. Safe example. Let's do it. Safe example. And that's an sts of string. Okay, now we're like actually using it, so that's good. Safe. Oh, it doesn't have it. Find it. Safe example. Thank you. Do, and then so we want to obviously press the right key, please. New. So we're going to create a new stref, and we're just going to say hello. So it's a string. Yeah, so our stref, so if we look at new stref, that returns us an st of s, stref, s of a. So that'd be like a whatever string there. Okay. Hold on. Yeah. So we're passing in string. So stref, so look. New stref takes an a and returns us that. Okay, so our a is a string, and it turns us an sts of stref of s of string. Whoo. I guess we'll see if we hover it over here. No, right. Oh, I've not saved it, so it's not gonna show us anything right yet. And then we want to modify this. Let's modify what we've just created. let's modify our ref. And to do so, if we remember, it's modify ref takes a function of a to a, which plus plus like that. If you remember, plus plus takes takes two values, but we're partially applying one, so it expects another value. So ideally, we're doing that a to a. We're passing it on. We're doing plus plus world to hello within this ref. Okay, that's fine. And now we've done that, we can read it. So there's like a little, you can see where there's less passing things around. We can just literally just do it. Yes, at this point, you can clearly see that, you know, we're only reading it again to just grab the value out. So this should be proof that it's been mutated. Because you shouldn't be able to just grab the same ref here, mutate it. So, you know, if this wasn't like if we won't be able to mutate those, that'd be the same result as what you got out of here. But here this should just be hello, if it weren't mutable. But this should be proof that it should say hello world. Come on. We'll do that. We'll reload, and we'll do run. You gonna find it? Why? Ah, it's not gonna find it. Why not? Okay, let's do load then. I'm pretty sure we already had it. Oh no, we haven't. So chat 0. Okay, there's nothing in there. Okay, how do I know? Let's just get rid of it. Kill it. Kill the whole session. Kill that. Do this. Okay, I've just got to load up. I did the repo in the old. Did I do it in the old one? Yes, I did. I did it in the old file. So we've got to load again. Though I thought the other one should have done it, but never mind. There it is. See, now we can see it. Cool. So run. Yeah, can find it, and then save. So let's hope. Hello world. Whew. Okay. So that made a bit of sense. But now we need to know about what this is doing here, because that's the magical trick it was saying. But this type system now prevents us from run STing any code that would leak a reference to sref. Oh, okay. So we can't simply do that. So look what for what reference? Because I don't know. Let's have a look. So I mean, it makes. Is it because our new stref is not inside? Oh. Yeah, that's the same. So couldn't match the type with type A with stref s bool. Okay, because type variable s would escape its scope. This rigid column type variable is bound to a type expected by the context for all stsa. Oh, expected type stsa, actual type sts, stref. Oh, okay. I think it's coming together. This is actually like a good error message. Bloody hell. I wasn't expecting one of them. Okay. So let's go up a little bit. Indeed, run st seems to work as expected, but how? Let's look again at the type of run st. Yeah, so this is the bit. This is where it's happening, and it's something to do with this s, this phantom type. What is it? The word for all here acts as a quantifier over s. Okay, the type variable exists in scope only within stsa because it's existential without a quantifier. We have no way of talking about the type. It simply doesn't exist outside of its for all. So yeah, that, oh, okay. Because we've got the for all s in here, but if we had it in here, then the trick wouldn't work, you'd imagine. Then we're like, Kitty! Don't worry, my cat. Sorry. I make a weird noise when I see my cat. Yeah, there we go. Now we're not happy. I mean, yeah, now things break. Okay. Oh, it's like the tension of the music's coming to resolution. Okay, and this is a secret why the ST trick works. We exploit the fact that extensions can't leave their quantifier in order to scope our data. The quarantine zone. So in here we're quarantined, but running it like this, we're not, because the new stref is out of quarantine. It's not inside here, I think. Okay, let's keep going. It's defined with existential quantifier. We tag our quarantine data with the result existential type. So here we do that, but here we but in here we don't. Yeah, okay, I think. Yeah, I think that's the idea. So here we're able to say that that's STS of string, but here we're right. So it quarantines the S inside of here, which is what we're doing by using this. But when we're running it like here, we're not giving any S, and there's nothing quarantined at this point. Is that right? Yeah, I think that's right. I don't know though, but hold on. This new refst should return this new. Where is it? New refst. Okay, yeah. So that doesn't even return us anything good. That would be of use. We need this. So A should be sref sa, but what is S? Well, it's a phantom. It's nothing. This little S here and there and there. But I guess it's because, isn't there further up here where it's needed on both sides? And that's what like binds them together. Because it can't do one without the other. Is it here? Well, it's certainly here as an example. So it's there and there. So it relies that if that one's there, that one also needs to be there. Okay, maybe it explains a little bit more. Let's read on. It's defined with existential quantifier. We tag our quarantine data with the result existential type, and the type system does the rest. To really drive this home, let's look at a specific example. Take again the case of run st new ref true. If we specialize the type of run st here, it results in the following. Oh, okay. Oh, of doing... Okay, so of doing that, what is the type of that? Can we find out anyway? Would the compiler give us anything back? I guess it won't. It'll probably just... Yeah, it won't do it. But imagining we do. So it's a for all S, STS, sref bool. Okay. The result is the following. Written like this, it's more clear what's going wrong. Oh. Is because the for all still... No, it can't. Just tell me. Written like this, what's going wrong. The type variable S is introduced and scoped at 1. Yes, so that's because it's inside. And then this ref doesn't have access to it because it's here, I think. Is introduced and scoped at 1, but later S is referred at 2. Oh, okay, yeah. At this point, the type no longer exists. There isn't any type S in scope. Oh, I got a yes. GHC calls S a rigid scolum. Yes, scolum. Type variable. Rigid variables are those that are constrained by type signature written by a programmer. In other words, they are not allowed to be type inferred. A human has already given them their type. A scolum is, for all intent and purposes, any existential types. Mathematically, I'll zoom in. Mathematically, it's an existential quantifier, variable expressing the terms of for-all quantifier. Since in Haskell we have only for-all quantifiers, all existential variables are necessarily scolums. Okay, keep note of that. So I won't remember. Okay, GHC given. Where's 1? Here we go. The purpose of a phantom S variable in ST and STREF is exactly to introduce a rigid scolum. If it weren't rigid or specified, it would be free to vary, and Haskell would correctly infer that it's unused. Infer that it is unused. Oh, okay. Ah, okay. If it were a scolum, we would be able to restrict its. If it weren't, sorry, a scolum, we would be unable to restrict its existence. This ST trick can be used whenever you want to restrict the existence of some piece of data. I've seen it used to tag variables owned by external FFI and used in implementation of monadic regions, which have more of a fewer effect capabilities. Wow, well, there you go. Chapter 8 rolls. I'm hungry. I need food about after that one. So what? Hold on. So I wouldn't mind. See, the thing is what I try and do is once we've got one viewpoint, I try and get another one. Existential types. Does anyone know of a good blog post? Oh no, hold on. Well, we had your good blog post, didn't we, SuPP? We had. Don't lose it. We had this one. So that's for the equational reasoning. I need something next to do with existential. Look at that, capital letters. Don't do in types, just do in Haskell. Tutorial? I mean, it depends how many people call their things tutorial. Oh. But that's... No. Okay, well if anyone... Oh, here we go. Maybe. 2016. I always try and look for something a bit newer in case it's using naturals. And then I look at it and I go, is there more code than writing? I'm so bad, aren't I? Medium. Maybe there'll be something. Yeah, I'll look through, see if there's something else. Oh, does it? I was going to look at that. I took interest to that actually. There. No. Functional game. Yes. Slides. Talk. Oh, you did a talk. Yeah, that's the ones I prefer. Sweet. Keep that for this afternoon. Thank you. Yeah, I'll have that. This is, for me, the best format of learning is videos. But just all the stuff that I want to learn isn't really on videos. And the best format I like watching is people literally going through code and trying to explain bit by bit. Again, that's another hard format to find, isn't it? I guess it's only Twitch. But yeah. Well, I've got a few things. I'm definitely going to watch this. That kind of looks a bit wrong. Flip. Yeah, it looks a bit like a phallus, but I won't go into that. Cool. So the sleigh and there's the game. So it's Dino Rush. Hold on. GC performance in his game. So I decided to just go for it so I can see if I can make it work or not. Well, I know I'm adding to the space I like. It's kind of helping me out, I guess. Or yeah, I guess other people get to watch me struggle. It's great, isn't it? It's better, I guess. It's been better on the simpler stuff, like doing the learn for Haskell. That's been fine. Yeah, thanks. Cool. Well, thanks for coming and helping out as well. I feel like maybe we all learnt. I don't know. Maybe not Sue PP. Sorry, but thanks for helping. But next time will be roles. I've got to spend some time carrying on with Learn Haskell because I'm only one chapter away. So yeah, I'll have to do that at some point. And I'm going to do some more. I think maybe after I've watched your video, I'm going to do some more animations because I feel they bring like just an edge, like a what you doing type of edge. What this isn't Haskell. You're not going to do stupid stuff. We're all serious developers, but we're not. Cool. Right. Anyway, on that note, yeah, enjoy this one. This other weird drawing I've done of what I look at, sort of, and see y'all's next time. Bam.